Hi, I'm Ashley Ross, and I'll tell you a bit about how we construct large-scale structure catalogs from Galaxy Redshift surveys, and hopefully give you an idea of the observational issues we might want to worry about when thinking about measurements of parity violation. So, first, just some basic definitions to get everyone on the same page. Uh, Galaxy Redshift survey is just a collection of observed redshifts. So we have the angular positions and the measured redshifts for some set of extragalactic sources. Um, Here we're using quasars synonymously with galaxy. Uh, Quasars are just as good. And, and usually these surveys would actually be planned with some strategy, but in principle, this could just be any collection of the angular sky positions and redshift measurements for some set of galaxies. And then the actual large scale structure catalog is adding value to that galaxy redshift survey so that we can robustly measure fluctuations in those galaxy counts so that we can essentially measure clustering statistics, endpoint functions, uh, power spectra, etc. And often this would just be a matched set of random angular and redshift positions. We often attach some weights to the galaxies and randoms, either to make everything more uniform and also to optimize the signal to noise of any particular measurements. And so the premier example of the galaxy's redshift survey right now is DESI. I do most of my work for DESI, so any excuse to show off this plot. So this is just a very narrow slice through the DESI data right now. You see the different types of galaxies uh, we observe with DESI over a wide redshift range, and you see the beautiful cosmic web that it maps. And you can see in the middle here where we covered everything quite well. You could probably just put a uniform distribution of randoms, and you look at your fluctuations relative to that. So it all sounds easy to start with, probably. So why does this actually work? So the whole idea with the reason why we think we measuring the fluctuations in the counts should be interesting is we have the cosmological principle that there's no preferred direction or place in the universe. It's isotropic and homogeneous. But Galaxy Redshift survey will never be either. Um, and you might have noticed we clearly didn't have a slice there of the whole sky there, and what I just showed you, for example. And so the work is to actually try to determine the expected number density uh, at all places where we have observed um, and all redshifts. And uh, so there's a bit of work that goes into it. So um, first is just clearly we have not uniformly covered the whole sky with any of our surveys, um, and even within the area that we cover, well, we're going to have to mask regions where we have bad data or bright foregrounds. Um, Similarly, the conditions under which we observed our data are not going to be perfectly uniform. We're not going to have the same signal and noise everywhere on the sky, and that's going to affect our survey efficiency, and affect the number density of galaxies that we expect in different areas. And we also might not be able to simultaneously observe two galaxies very close on the sky to each other. If the two galaxies are too close together, for instance, we often place fibers next to each other in the focal plane to get redshifts. They can only be placed so close to each other, so we can't simultaneously observe those close pairs. And that will put in an incompleteness pattern that is actually modulated by the actual sky density. So it's connected to your clustering measurements. And so just for a clear example, we look at this DESI data again, and you can see varying sized holes, just gaps in our coverage. That's isotropic. Some of them are very obvious, and some of them, you can see it look like they're affecting one type more than another. That'd be a completeness variation. So, that, basic idea of why things are anisotropic. But you should also be able to see from this image of our DESI data that what we observe is not homogeneous either, and for the basic reason that there's redshift evolution. We expect the universe at any given point in time to be homogeneous, but things evolve with redshift, structure grows, the relative matter density changes, and simply we observe everything within a particular wavelength on Earth, and the rest frame wavelength that corresponds to at a given redshift changes. That's the concept of redshift. So for a given spectral feature, there'll be some range in redshift that we can observe it in, and it'll be at a different wavelength in a detector at each of those redshifts. And our detector is obviously going to behave differently as a function of wavelength. And so one sort of obvious thing would be, so if we have an emission line, like for DESI ELGs, we use the O2 doublet, which is at about 370 nanometers. And we can observe that to a maximum redshift of about 1.6, because the maximum wavelength covered by DESI is 980 nanometers. And so we cannot observe any ELGs with our instrument above redshift 1.6. So we'll have a very obvious inhomogeneity in our sample. So for the basics of the anisotropy, we just have to know where we actually could have observed, where we put those holes. And so that basically just means tracking everything that we do quite well, and validating that we've done it. So for DESI, we want to know everywhere on the sky that we could have possibly gotten a redshift. And we can use the DESI software to do this. There's this fiber assigned software that says for given conditions and of the instrument, where could we have placed fibers on the sky, and we can test random points with that and find out which ones we could have actually placed a fiber on, and that gives us our footprint. And then thinking of something use a grism like Euclid or Roman, there, the spectra are light dispersed by the grism, and you need some kind of reconstruction from where you see the spectral features on the detectors to the sky position they correspond to. In order to reconstruct the sky position from what you observe from the grism, you'll go in one direction. You should be able to go in the opposite direction to take a random point and say, where would this line have showed up on our detector if it was from a galaxy at this given position. So that requires mastering your collaboration tools, but that's all it requires. You just have to make those tools efficient enough and easy enough for everybody to use. And then for the radial distribution, so the inhomogeneity that I was describing, there the problem's somewhat more difficult. So here on the right, this is the actual co-moving number density that we observed in our early DESI data for our different DESI samples. And none of these curves are things we're going to be able to predict from first principles. Maybe our BGS samples because they're flux limited, but the other ones, there's basically no way to predict that for first principles. And so the easiest thing to do is actually just randomly assign redshifts that you have observed to your random points, and then the random points that you use as your reference sample to measure fluctuations against will have exactly the same redshift distribution as your data. Because it's exactly the same, that introduces an extra integral constraint, radial integral constraint. But that's something that we can fairly straightforwardly introduce into any of our modeling, and therefore account for at the cost of losing a small amount of signal inputs. You lose any clustering information that's purely radial. But unless we can predict what the N of Z would be from those first principles, we're going to be losing some of that no matter what. And any kind of spline or whatever through, you would have to model the impact of. So the easier thing to do is just accept this radial integral constraint. And so when planning the surveys, the common thing to do is make a selection that we believe should give us a relatively, at least, isotropic sample. And the way that this works in SDSS or DESI is that we have what we call our targets. We have imaging data from which we pre-select the targets. We make cuts on that imaging data, and we then go ahead and get the redshifts for as many of those that we select as we can. For Euclid or Roman, we won't have any pre-selected targets. You get everything on the grism, but you'd imagine that you probably want to be cutting above a certain line flux that is safely above a given detection limit, or require 2 lines or whatever. You'll probably want to be adopting some kind of cut, unless you really want to go into the complications of modeling exactly how your distribution is going to change as a function of, say, the line flux threshold. And though these cuts should help in giving you a sample that you should be able to model and should be relatively constant, there's always going to be scatter in these cuts, and that scatter will introduce anisotropy in your sky distribution. And one easy way to understand this here is just using number counts of detections in the photometry from the DESI legacy survey data. And you can see that we have dramatically more counts of faint objects than bright objects. So if we cut at any given flux, so say we cut at G-band magnitude of 22 here, we're going, so the scatter might be Gaussian in magnitudes or in flux. Either way, if that's Gaussian around something that's rising like this, you're going to get more of the fainter objects scattering in than the brighter objects scattering out. And that'll be true anywhere, but that'll be amplified if your uncertainty is greater. If the uncertainty on your photometry is greater, if your photometry is less deep, as we like to say, you'll get more scatter. And for something like a flux threshold, that increase in scatter will actually increase the number of galaxies in your target sample compared to the more precise photometry. And typically, we're not just cutting on one flux. Typically, we have some fairly complicated color cuts in order to isolate particular types of galaxies that are, say, likely to have emission lines. So this is the color selection box for the EBOS emission line galaxy sample. And so we're going to get scatter along any of these selection cuts. And so in order to model this, we start turning towards simulations, and we look at the actual scatter, and you can see here for EBOS that the greatest scatter is along this particular color cut here on the left-hand side, and those galaxies scattering in are faint galaxies at lower redshift. So this meant that our EBOS sample, where the depth was worse, had more galaxies at low redshift, and we had to account for that in our analysis in order to not get biased results. And so often we call all of this stuff just observational systematics. And these observational systematics, these are basically the properties of the observed data, how we observe the data, that cause these sorts of fluctuations that are going to give us these anisotropies. So right now, so up to now, we really just discussed how the impact of noise will be asymmetric, that you'll get oftentimes more scatter in than out. We'll go through a whole variety of kinds of effects in a minute. But one thing to note, I kind of discussed in the EBOS case, even though these will all be plane of sky effects, these will couple to the radial distribution, because there's no reason to expect that the change in the number of galaxies that we observe with these fluctuations to be even with redshift. An example, the EBOS ELGs that we just discussed, it wasn't even with redshift at all. The scatter was predominantly at low redshift. And so this is something that you have to pay close attention to. So I think it's useful to divide these systematic fluctuations into um, three chunks. So the data quality variations, uh, basically what we've been discussing so far in terms of the changing signal to noise. The way that the signal to noise changes, there's a number of factors that go into that, and those factors can matter, but effectively it comes out to signal to noise. Then there will be foregrounds, things like bright stars that we corrupt our ability to measure anything around them, or as those stars get to a, say, medium brightness, let's call it, they're not going to completely corrupt everything around them, but they will affect it enough that we might need some statistical correction. And then things like dust in the Milky Way that extincts light, or emission lines from the Milky Way itself that can actually get in our galaxy spectra and mess those up. And then there'll be calibration uncertainties. So basically, how good is our relative calibration on our photometry or our spectroscopy from place to place on the sky, and how does that induce fluctuations in our galaxy counts? And so all of those things can matter both for our selection of what we call good redshifts in the galaxy survey, and modulate the target density. But we can kind of roll them up together. And then we did mention earlier that the fact that the completeness variations are coupled to the density in DESI, and probably also in anything with a GRISM, where you'll have more line confusion if you have overlapping spectra on your detector. It'll probably be harder to reconstruct the sources that they came from. So in order to see the sorts of things we have to do to correct for that, you can look at this Bianchi et al. Paper. And then we also need to worry about catastrophic redshift errors or interlopers. So that could either be, for instance, with DESI, it's actually a skyline in our spectra, and it's been falsely identified as an O2 line, and so we just assigned a completely wrong redshift to one of our galaxies. In space, we're worried about interlopers, not knowing actually which emission line we're actually looking at, and therefore having the wrong redshift for an actual galaxy. And those will bias the clustering that we measure. Those you can't really treat on the catalog level. You can only try to estimate the rate, any bounds on what that rate could be, and then simulate and model the effect. You can try to make the rate as small as possible with your quality cuts in your catalogs, and we do that. But then, after you've basically optimized your purity metric, then you have to deal with the consequences in the model. So we'll mainly be discussing the sorts of items at the top here the rest of the way. So for the data quality variations, this is the kind of thing that we've been talking about already, where the depth of the photometry might be changing. But the reason that the depth can change will come from numerous aspects of the observations, and those will affect different types of galaxies differently. One example is the size of the PSF, um, depending on how extended a source you're trying to measure the photometry for. The PSF size will affect that your ability to measure that differently. So the details do actually matter. Um, these quantities, we're able to record them and map them quite well. Here's an example of just the seeing distribution from Sloan DR7 photometry. So this is pretty old data, but it shows a nice map where you very clearly see the observing strategy of SDSS. It was done in these stripes, and so you see a striped pattern in the difference in the seeing. And so a nice example of exactly how strongly the simple changes in the depth of the photometry can affect our galaxy counts were the SDSS EBOS quasars. These were the targets were selected with an algorithm that was based on the probability of an object being a quasar, and you're able to have a greater probability of being a quasar if the imaging data is better. So where the data is deeper, in this case, we observe more quasars. So we're looking at the relative density of quasars here against, this is the G-band depth. We could have looked at any of the bands used in SDSS, and you see there's a strong trend. And we correct these trends in the data, and that's what the green points show. But clearly a fairly large correction was needed. And so for foregrounds, that's basically the Milky Way, traced in many different ways: stars, dust, whatever, different kinds of emission lines. So these will be static. We can improve these maps all the time through better measurements of the structure of the Milky Way. And every time somebody comes up with something better, we try to fold that in. And so there's just Planck, if you just look at it in this wavelength range, it's got quite some structure from the galaxy there, and you can imagine any of this structure modulating what we're actually able to observe. And one thing we learned in EBOS about was the importance of exactly how these foreground maps can be reduced. So now, ancient history, 12 years ago, we saw a strong effect in terms of us observing having less boss targets close to stars, fairly faint stars, and we corrected for that effect with maps of SDSS stars. And we kept using those maps for 10 years. And then we realized, when we were still using those maps, comparing them to the EBOS quasars, that we really needed to update those maps, in particular for quasars, because quasars are point sources, and the maps of stars are basically just maps of point sources, so probably some overlap there. But we also had a better way to trace the density of stars through data from Gaia. So we actually learned that we needed to do that to correctly model the fluctuations we were seeing in our quasar density. But probably the hardest issue to deal with are the calibration uncertainties, because these these are just uncertainties. They're unknown. We can try to quantify how good our calibration is, but if anytime we can make a map of our actual calibration errors, well, we're going to fold that back in and correct them. That's what that's what the calibration is. So we can try to use that to say what the remaining level of fluctuation could be, and we do. And this comes up in a number of cases. One obvious thing is just the relative photometric calibration, what we call 0 points. But we're always subtracting sky background from images. That requires some estimation and subtraction. The actual PSF size we use in the modeling of the photometry, that actually requires measurements of stars. We have to know, and we have to know our optics very well. And then we just treat that as a known. And then finally, one of the things that is a foreground, we try to turn into a calibration. We know the dust extincts light from galaxies that we observe. We measured the dust, so we go ahead and correct our measured fluxes based on how much dust there is. But that depends on how well we've calibrated our maps of the dust and how that translates into changes as a function of wavelength. So that is a calibration issue, and this is an issue that we're looking into from a lot of angles right now, because it can seriously impact our measurements in a few different ways. And one of the ways is actually the dust maps themselves can be contaminated by galaxy light and have actual large-scale structure in them. So if you're not careful, you can actually be subtracting real structure from your measurements when you try to subtract out the dust. All right, so a little bit more, how do we actually try to correct this? Well, we roll everything together and we say, okay, given everything we know, let's say what the number density of our galaxies should be at that given position, and then we can calculate over densities. We can look at relative fluctuations in the galaxy counts. And one thing that's true is all of our methods that we use to determine basically, so this n bar is basically what we call our selection function, and basically all our methods we use to determine that we need to calibrate some way in mocks. There'll be biases no matter what. And so we have to try to calibrate them and then figure out a way to marginalize over any remaining uncertainties. And the effect of the corrections tend to appear greatest on large scales. So here at low L, so this is an angular power spectrum. The largest scales are low L, and this nice plot from Metis showing how the systematic effects can mimic the effect of primordial non-Gaussianity. But you can see at the larger L, the smaller scales, we have a fairly small effect. And that tends to generically be true, though you shouldn't just always assume that it'll be identically true. And so one approach is to use maps and regress out the trends that we find, comparing the number density that we observe along this observing property vector. And there's a bunch of methods that come out over the years, making things increasingly non-linear, taking more and more advantage of good machine learning approaches, and et cetera, et cetera. But the bottom line doesn't change that we need to calibrate all these methods. There will be biases no matter what. So an example of making the methods more complex and how that was actually necessary was this analysis Resi et al. On the EBOS quasars in order to get more robust measurements of primordial non-Gaussianity. This more complicated neural net regression technique was needed. But there will always be limitations. One, do the maps you have that you use for the regressions form a complete basis of the systematic fluctuations? That's hard to ever know. Are the maps themselves okay? We know already. We mentioned how the extinction maps will have cosmic infrared background. They'll be correlated with real large-scale structure. In DESY3, we created a huge number of PCA maps and then found that some, when we got to high number on there, they were clearly correlated with actual real structure. So there is some danger there. And even when you aren't correlated with real structure, you'll have chance correlations. You'll be removing some true clustering modes, and so you have to calibrate that. And then any calibration uncertainties themselves won't be captured in these maps unless we're lucky that the maps are somehow proportional to those. Approach that has is becoming increasingly used is to forward model the variations that we see, and this would so when we do this in the imaging data, this is actually injecting the galaxies into the imagings, and then for DESY doing something like repeating the target selection, and so this depends on your calibration being correct, all the estimates of how the sky background worked and the PSF, etc. But if you do this and you inject enough galaxies and you're careful not to make them overlap in ways that mess things up, this tells you basically exactly about the data quality variations without having to do regressions based on those. But it requires injecting a lot of galaxies into images. This was an early example of applying this to just a photometric galaxy survey, early dark energy survey data. I think something we'll increasingly use is this sort of hybrid approach where hopefully we can use the forward model to eliminate the need for maybe all the maps and just regress out residuals after using the forward models. And so an example here is this is a DESY image simulations for using for LRGs where the trends with the data quality are reproduced quite well. There's the depth and PSS size variations. Some of the trends with the foregrounds are not, but if we just potentially use the forward model for the data quality variations and regressions for the foregrounds, then maybe we've removed less from the regressions. Right, so there's that should give you an idea of the kind of work that we do. It's not comprehensive run through it all, but probably enough for a start. And so this meeting's about parity violation. Could any of this actually cause parity violation? We're mostly talking about um, effects on the sky. I mentioned earlier how these will couple with the radial distribution. So potentially there would be those three-dimensional effects there, and I think at the very least you'll have issues with the noise. So you want to take a close look at it all, and then just thinking about parity violation, thinking about handedness. Do we have handedness built into our observations? I mean, we do. The Earth spins with in a given direction, and our observing strategy for any telescope on Earth is very much tied to how the Earth is spinning, and then we orbit in in a very particular direction as well, and what we can observe at a given time of year obviously changes, and then the conditions that you're observing, those will typically be different in the middle of a night, at the beginning of a night, at the end of a night. You'll have different things like the relative ambient temperature to the mirror temperature. All sorts of things like that will be changing over the night, and that will always be going in one direction. So can any of that translate into anything that's a parity violation in a galaxy survey? Can't think of a specific way, but there is that handedness built in, and of course anything we have in space, we still have, we're still orbiting there at L2 in a particular direction, and the telescope and detectors are all in a given orientation always. So I think there is always an asymmetry there in the actual instrument. So can any parity violation in your observing setup translate? I don't know, but hopefully it gives people things to think about. So feel free to ask any questions over email, and I promise to get back to you someday. I hope to be there for the meeting, but I can't guarantee it. So sorry if I'm not able to be there. All right, thank you.